Okay, now we are in Newton's laws of motion. We have three laws of Newton's law. Okay, we have Newton's first law of motion, and then we have Newton's second law of motion. Thirdly, we have Newton's third law of motion. Okay, basically, Newton's first law of motion is about equilibrium. Okay, total F equal to 0, total force equal to 0. Newton's second law is about acceleration. Yeah, total force equal to ma. Total force equal to ma. And then Newton's third law is about action-reaction force. That is in short. Okay, now let's go deeper into Newton's first law of motion. Okay, Newton's first law of motion states that if there is no net force acting on an object, so if the object is at rest, it will stay at rest. If it is moving, it will keep on moving at a constant speed, at a constant velocity. So what I'm trying to tell you is, let's say, okay, let's say here we have let's look at the first one. If it is at rest, it will stay at rest. Like this ball, yeah, like this ball. This ball is at rest, velocity 0. Okay, so but before we look into this one, we need to know what do actually force do. Yeah, what do actually force do? So what are the 5 effects of force? We should know about this also. What are the 5 effects of force? Yeah, what can a force do? Yeah, a force can move a stationary object. It can move the objects. Okay, a force can also stop a moving object. Let's say an object is not moving, is stationary. A force can move it. If an object is already moving, a force can stop it. A force can also change the speed of a moving object. Maybe accelerate the object or decelerate the object. Okay, slowing down the object or speeding up the object. Yeah. A force can also change the direction of a moving object. Yeah. Maybe the object is moving to the left. Now you change the direction. A force can change the direction to the left, going to the right. So a force can change direction, can change the speed, can change the direction. A force can also change the shape and size of an object. That means like a force, you can compress a sponge. Yeah, let's say you grab a sponge, you compress a sponge in your hand. Yeah? So a force can change the shape of the sponge. Even like the impulsive force during the accident can deform the car, isn't it? Can change the shape of the car. It can deform the car. So during accident, that's the impulsive force. Okay. So these are the effects of force. So right now we have no net force. No net force, that means no resultant force. Bear in mind, this no net force doesn't mean that the object has no force at all. The keyword here is no net force. It doesn't mean that no force acting on the object. There is force, there are forces acting on the object, but just that it does not have resultant force. The resultant force becomes 0. No net force, it implies that still it may have, or what I can say is it may have or not have forces acting on it. May have or not have. It may have forces acting or may not have forces acting on it. Yeah, Now, one example is like this one. You see, this object, we cannot say, oh, no net force means no force acting. No. You see, like this object, it is stationary, velocity 0. It is sitting comfortably on the surface of the table. Okay, there is still weight. You see, there is still weight acting on the block, normal force. You see, and then there's external force pushing the block to the right, but then there is a static friction holding back the block from moving. So is there any force acting on the block? Yeah, is there any force? Yes, there is forces acting on the block. There are even 4 forces acting on the block. It just doesn't have any resultant force. It's just that when we total up, when we total up the x component forces equal to 0, because they cancel off each other nicely. When we total up the y component forces also, they cancel off nicely. No resultant force in x component, no resultant in y component. So these two conclude that no resultant force at all acting on the block. This is what we mean by no net force. So no net force doesn't mean that no force acting. No, got force, just that no resultant force. That means all forces balance. All forces balance. Balance means the force, what I can say is a force to the left. The force to the left equal to force to the right, and then force upward. Force to the force upward equal to force downwards. Balance. They cancel each other. You see, force to the left equal to force to the right. Force upward equal force downward. They cancel nicely. All right. The left force cancel by right force, so that's why total Fx equal to 0. The upward force cancel by downward force, so that's why the total y component force is 0. So when we these two combine, we get total force equal to 0. Result in equilibrium. So equilibrium is achieved when all forces are balanced, left and right, upwards and downwards. Okay. So no net force acting means balanced force. Okay, equilibrium. So first law is about equilibrium. Yeah, equilibrium. Total force equal to 0. Yeah. That means 0 resultant force in x component and also 0 resultant force in y component. So if no resultant force acting on the object, then what happens is, if the object is at rest, it will stay at rest. That means this condition is about static equilibrium. Total the velocity equal to 0. That means if the object is at rest, it will stay at rest forever. Like you see this ball, velocity 0 is resting. Okay, so resultant force is 0. Okay, so it will stay at rest. If there is no resultant force at all. Okay. So no resultant force at all, or can say maybe we didn't push. No resultant force at all acting on the object. It will continue to stay at this condition all the time. Yeah. Finally, the velocity is still 0 forever. Yeah. It achieves static equilibrium. But if let's say the object is already moving, then if there is no resultant force, if there is okay, like just now stationary, isn't it? Stationary. Okay, if the resultant force is 0, it will continue to stay at 0 velocity. But if it's already moving with certain velocity, okay, let's say velocity equal to 10 meter per second. So the resultant force is 0, let's say balance. Again, it will still move with the same velocity, also move in the same direction, 10 meters per second, if no resultant force. Understand? So this one, for this case, this one is velocity constant all the time. Velocity constant all the time. Yeah. It keeps on moving at a constant velocity. Velocity doesn't increase or decrease. This one is called dynamic equilibrium. Okay, when velocity is constant. Yeah. So when velocity zero is called static equilibrium. When velocity constant is called dynamic equilibrium. You see, for this these two, you can see that velocity doesn't change. Yeah, for these two, velocity is zero, velocity constant. Yeah, these two, that means it has one similarity is velocity doesn't change. There is no change in velocity, isn't it? No change in velocity. So when velocity doesn't change, means acceleration zero. Acceleration zero. So this acceleration zero relate to total force equal to zero, because we know that when total force is actually equal to ma, isn't it? So when total force is zero, when net force is zero, that means the acceleration also zero. Like mass times zero is equal to zero. So when no net force, resultant force zero, so the object will not have any acceleration. The acceleration is zero. Because acceleration is zero, that's why velocity is always zero. At rest, stay at rest. No acceleration means the it stay at rest. Okay. No acceleration, zero acceleration, no net force, no acceleration. Like an object is keep on moving, the object keep on moving moving, it will also keep on moving at the same velocity, at a constant velocity. Yeah, velocity doesn't change. Yeah, because net force zero, acceleration also zero. When acceleration zero, velocity does not increase, does not decrease. So velocity remain constant all the time. If it is moving, it keep on moving at the same velocity. Yeah. So when we can say that when total force is zero, yeah, because we know that a force can move the object, can stop the object, can change the speed, can change the direction, can change the shape. So on the other hand, if total force equal to zero, what can we say? We can say that when total force is zero, so there are no force on it to move the object, so the object will remain stationary. So when resultant force zero, yeah, resultant force zero, the stationary object will remain stationary because no force to move it. It will remain stationary. Same thing, like total force zero. When total force is zero, that means a moving object, there is no resultant force to stop the moving object, so cannot be stopped. The object will continue moving, So if resultant force zero, no force there is force. Yeah, actually there is force, just that no resultant force. Okay, if resultant force zero, that means cannot change the speed also, that means the speed remain constant. This one speed remain the velocity remain constant for a moving object. Now how about if resultant force zero, moving object, also the direction cannot change. It maintain at the same direction, the velocity remain, or we can say the object still going in the same direction, because resultant force zero, no force to change the direction of the moving object, so it will remain at the same direction. So when resultant force zero, also cannot change the shape or size, that means same shape, it remains at the same shape or same size. Remain at the same shape or same size. So okay, that's it. Yeah, that's it. What it means by Newton's first law. Another thing is about this one, mass and inertia. Okay, mass and inertia also mentioned in the Newton's first law. What it means is a bigger mass will have bigger inertia. Like you see, you compare a mouse, a mouse with an elephant, okay, with an elephant. An elephant, how to draw an elephant, okay, see the trunk. Okay, so which one has a higher inertia? Yeah, let's say both are running. The mouse are running, the elephant also running at a very high velocity. Okay, so which one is harder to, which one has higher inertia? Which one has higher inertia? Of course, the elephant has higher inertia, yeah, because of the mass. The mass of the mouse is so small, but the mass of the elephant is so high. So end up, we can say the inertia, yeah, just put inertia. So the inertia for the elephant is much higher. The inertia for mouse is much lower. That means we can say, you know, the elephant is harder to stop. Okay, it's harder to stop. Yeah. So because it has higher mass, higher inertia, harder to stop the elephant from moving, compared to the mouse, easier to stop the mouse from moving. Yeah, because it has lower inertia. Yeah. This one will keep on, because it has a big mass. It tends to keep on moving at a constant velocity. Yeah. Because it has very high inertia, very hard to stop it from moving. Also, if you want to move the elephant from stationary condition, also harder to move the elephant compared to the mouse. Mouse easily you can just kick on it, if fly off to the sky. Yeah, but elephant, how going to kick the elephant? Yeah, elephant has such a big mass and such a high inertia. You also very hard to move a stationary elephant. Okay, so sign convention. Lastly, I want to talk about the sign convention. Yeah, we maintain. Yeah, because usually we take going to the right is positive. Yeah, going to the right is positive. Going to the left is negative. Yeah, going upward is positive. Going downward is negative. We maintain that way, isn't it? So very easy. Yeah, we maintain the same thing. So if we saw in equilibrium objects, yeah, let's say this. Okay, where is the okay, this one. Let's say this object is equilibrium. Okay, let's say this object is equilibrium. One example, I use this one. Yeah, equilibrium. Okay, so we just take forces to the right as positive, forces to the left as negative. We just put like that. Forces to the right, just want to cancel first. Okay, we just maintain forces to the right as positive, forces to the left is negative, forces upward is positive, forces downward is negative. Okay, so how do we apply the positive negative sign? Like this, look at here, total Fx. So now let's say I want to find the total force in x component. Yeah, I have I forget to draw the axis. Okay, I draw the axis. This is the axis in x component, and this is the axis in the y component. Okay, so what are the forces exist in the x component? What are the forces exist in the x component? The external force and the friction, isn't it? So external force, we put positive or negative? We put as positive because it is to the right. So external force we put as positive. Put as positive external force. The positive sign you don't need to write also can, because we without the positive sign we know it is positive. Okay, but the negative sign you need to put. Negative sign you need to put. Yeah. So okay, so in the x component we have friction. Yeah, we have external force and the friction. So the friction is to the left. We put as negative. Put as negative. Okay, and then friction. And these two, since they are equal, external force and friction, since they are equal, so you see, external force minus the friction. So, and since they are both same force, equal force, so they cancel out totally. They cancel out totally. Yeah, because one positive, one negative, one positive, one negative, so they cancel. So that's why they get 0. So total fx equal to 0. Do you see that? Total fx equal to 0. So we also can okay, now look at the y component. Look at the y component. So how going to find the total force in the y component? Okay, so forces, we take forces upward as positive, forces downward as negative. So the normal force is going up, so it's positive, so put that as positive. And then we have a normal force, and then the weight is downward, so it's negative. Downward we put negative w, weight. Also the same thing, these two forces, they are equal. The normal force and the weight, they are equal, so they cancel off because one positive, one negative. Okay, one positive, one negative, so they get 0. Okay, so that's why when the force, they are opposite direction, one to the right, one to the left, they become minus. Yeah, one upward, one downward, opposite direction, they become minus. They cancel each other. You see that? They cancel each other. So because it is equilibrium, the force to the right equal to force to the left. Okay, they cancel each other, you get 0. Y component also, upward equal to downward, cancel, you get 0. So that's why we get total Fy also equal to 0. So in the end, this conclusion, we can say there is no resultant force. Total F equal to 0 when total Fx equal to 0, total Fy equal to 0. So total F equal to 0. No resultant force. We can further elaborate. This one. Okay. Like just now, total Fx equal to 0. It means that the force, external force, is the negative Fx go to the other side. We get external force equal to friction. And then this one, the weight go to the other side. It become N equal to W. So this is what it means by forces. This one is forces to the right. Forces to the right equal to force to the left. You see that? Forces upwards equal to forces upwards. Forces equal to forces downwards. So that's why they cancel totally. Total force equal to 0 in x component and y component. Understand? Forces to the right equal to forces to the right equal to forces to the left. Forces upward equal to forces downward. So total force equal to 0. Equilibrium. Okay, so that is remember the sign convention lah. We always put going to the right positive, going to the left negative, going upward positive, going downward negative. And that's all for Newton's first law of motions.